All right, so this talk, there were two strands to my research, and one kind of concerned space-time physics and kind of thinking about what I call space-time functionalism, and another concerns into theoretic relations, which is presumably the reason I'm kind of here today. And this, in some sense, is me trying to kind of square my thoughts about functionalism with thoughts about intertheoretic relations. Largely came from sort of thinking about things in the space-time functionalism literature, but I hope it's sort of more broadly applicable to certainly thoughts about how we might use functionalism to understand intertheoretic relations within physics, perhaps more broadly. You guys can be the judge of that. Let me get my slides. Oh, there we go. Slides to actually change. So here's the thought behind today's talk. So functionalism, particularly the kind of functionalism that David Lewis espoused, has often been seen as a tool for reduction. But if you dig around in the philosophy of physics literature, you'll find people talking about functionalism as having something to do with emergent phenomena, usually where emergence is meant in this fairly kind of weak philosophy of physics sense. So which is it? And this talk's going to look particularly at some recent papers written by Jeremy Butterfield and Enrique Gomes that say, look, philosophers of physics should drop the kind of emergence chat with respect to functionalism and focus on Lewisian functional reduction, and then we'd all be really clear and we'd know what we were talking about. I think there's something in that, but I also think that doing that exclusively misses some interesting features of a kind of more Dennett style functionalist thinking. So I'm going to try and explain what I think it misses, and then, because I think these things sort of don't work unless you actually have an example for which to apply them, I'm going to try and give you an example rather briefly at the end in space-time physics, which I think illustrates the way in which we might think of the relationship between functionalism, these two kinds of functionalism. Good. Okay, so functionalism is one of those weaselly words, like emergence, like so many things in this space. So what do I mean by functionalism? Well, I think that there's a recent paper by David Chalmers that I think sort of has a very nice metaphor for illustrating the way in which functionalism in general can be thought of as part of our efforts to kind of reconcile images at different levels. In his case, the distinction between kind of the manifest and the scientific image. And it perhaps makes clear why functionalism might be relevant in all kinds of bits of science, not just in pure philosophy of mind. So he says, look, in the Garden of Eden, things are exactly as they appear. Objects have colors in just the sense they appear to. You know, the leaves outside my room are really green. It's in exactly the sense that they appear to be. But of course, after the fall that comes with scientific knowledge, we know we don't live in Eden. And color primitivism, the idea that things have colors in just the sense that they appear to, doesn't seem to be an option. And a really natural response to something like that situation is to develop functionalism about the concept of color. We decide that colors aren't what they appear to be to us, they're instead whatever are responsible for our color experience. So whatever causes our color experience counts as a color. And what you get from that is a kind of realizer functionalism that doesn't have to imply a kind of metaphysical functionalism about colors. They can still be physical properties in the way that we usually think of colors being physical properties, but colors are just whatever causes color experience. So that's a thought about why you might be kind of interested in functionalism in general in science. Here's perhaps a sort of slightly less metaphorical way to put this. We often propose a functional analysis of a concept when you realize that that concept's problematic from the perspective of our current science. So you find some concept, for example, space-time, and you problematize it. You think, oh gosh, we don't really have a proper grasp on this concept, or it can't quite be what we think it is. And then you propose a functional analysis of it, and that allows you to reduce the problematic concept to a scientifically acceptable one. This is all sounding very Lewisian so far, by the way. And of course, some concepts are going to be functional and hence unproblematic from the start. It's very clear, I take it, that the concept corkscrew is a functional concept in a kind of unproblematic way. And presumably some scientific concepts are more like colors and kind of need a functional analysis, and the functional analysis might be deep and surprising, and some are more like corkscrews. But you might think that we're going to have useful functional analyses and functional concepts all over science. Now here is a puzzle. I mean, perhaps it only arises in the philosophy of physics literature, perhaps it arises elsewhere, I don't know. Philosophers of physics like to talk about functionalism, They often sort of hand wave, gesture towards functionalism to solve foundational puzzles. They don't very often give a kind of deep analysis of what they mean by functionalism. But it crops up all over the literature, and you find people saying both that functionalism leads to emergence and that functionalism leads to reduction. So here's a quote from a paper by Wittrick and Lamb about space-time functionalism called Space-time is as space-time does. They say, we will argue that this functional approach offers a promising avenue towards meeting the conceptual challenge of the emergence of space-time and quantum gravity. So you get this claim in that 2018 paper that if we understand that space-time is a functional concept, we'll understand emergent space-time. In direct reaction to literature like that, you then get these papers by Butterfield and Gomes that say things like, this paper gives our general framework for discussing functionalism. Following Lewis, we take it as a species of reduction. Now, I should say that in philosophy of physics, these two things aren't completely strictly incompatible. Plenty of philosophers of physics, including all four of the people cited on this page, believe that functionalism and reduction can occur side by side. But there's still something a little bit odd about saying we give functional analyses in order to establish emergence and we give functional analyses in order to establish reduction. There's at least a tension that needs to be kind of solved here. If we give a functional analysis of a concept, have we reduced it or have we established that it's emergent? What do we think we're doing here? The answer, unsurprisingly, is, well, it's a little bit complicated. In a sense, you've not necessarily done either, and it depends where you put the emphasis in your functionalism. I think that even Wittrick and Lamb, there have been a number of kind of helpful papers, I think, published about Wittrick and Lamb's paper, talking about the ways in which their claim that you can use something like a Kim-style functionalism to lead directly to emergence, it doesn't really work. And I think that they would probably even agree with that now. I think the idea that offering a functional analysis of a concept directly shows some kind of emergence is really rather far-fetched. And it's also true that Butterfield and Gomes are right in that functional reduction offers a much clearer framework and has a really good pedigree. And if we all talked about it, we'd be much clearer about what we meant. But the point in this paper is going to be that if we just do what Butterfield and Gomes recommend that we do and focus on Lewisian functional reduction, we're going to miss some benefits of an approach that has more in common with Dennett. And while that latter approach isn't itself going to kind of betoken emergence, it's going to leave more space for a kind of weak philosophy of physics-y kind of emergence. Okay. So what kind of functionalism are philosophers of physics talking about? There's a reasonable amount of agreement here. Philosophers of physics should focus on something like a realizer functionalism about the space-time concept. That's the kind of thing I was articulating with that Chalmers metaphor. But even once you've got that agreed, you can find at least two functionalist strands of thought in the literature. You have this kind of Lewisian functional reduction, Canberra plan metaphysics in Butterfield and Gomes, and you have something that I'm going to call in inverted commas Dennettian functionalism that crops up, particularly in David Wallace's work. And the main point of this talk today is to draw out how those two things relate to one another. They're not really incompatible approaches, but I think that to get the full richness of what people might be trying to do, even though it's less precise in philosophy of physics, I think you need the second kind of functionalism as well as the first. Okay, so believe it or not, slightly lengthily, that was my my introductory spiel, and here's the outline. So I'll start off by saying something very generally about what I take these Lewisian and Dennettian approaches to be, say a bit about how we might reconcile them, and then we'll go into this slightly quick, because of the slightly constrained time, example of Newtonian gravitation. Okay, so Butterfield and Gomes' first paper on this topic wears its purpose on its sleeve. Great title, Functionalism as a Species of Reduction. So where they stand on this particular issue is very clear. And what they're doing is responding, and I think they are rightly responding to issues in the literature on space-time functionalism, where people are very woolly about what they mean by functionalism. And they say the following, they say, look, we come to praise space-time functionalism, not to bury it, but people need to pay more attention to the following things. They need to pay attention to the fact that functionalism is a species of reduction, and they're particularly interested in reducing chronogeometry, what they think of as spatiotemporal phenomena, to the physics of matter and radiation. The fact that functionalism can uniquely define a concept by its functional role, or define lots of concepts simultaneously by their roles, and the idea that functionalism provides bridge laws that are mandatory, not optional. They're statements of identity that lead to Hegelian reduction. So the thing that they're emphasizing there is the importance of a kind of ternary relation in functionalist analysis. You start off and you pick a theoretical term that you want to give a functional analysis of, say space-time, or spatial distance. Then you're going to pick out its functional role in terms of its relation to other terms, potentially within that same theory at that same level. So you might take the language of some theory, say the language of a space-time theory with, say, matter into it. You divide the language into terms to be given a functional treatment, and those that we take it that we already understand. But you can define more than one term at once. And they acknowledge that that project of giving a functional analysis is really hard, really involved, and not guaranteed to succeed. There's a lot of very good foundational work that goes into that project, the project of working out how theoretical terms actually play roles in a given theory. So that's, two parts of our ternary relation. You divide your language into understood terms and problematic terms. And then your third part of the relation comes in by finding the realizer of the functional role in a reducing theory. So for them, this is 100% a form of reduction. And then what you have when you finish that process, that difficult, hard, foundationally illuminating process, is a bridge law in the Hegelian sense. So you get a statement of identity between a term in the top theory and a term in the bottom theory that provides a bridge law in the Hegelian sense. So on that picture, and also, to be fair, in the picture we introduced in the beginning, the whole point of functionalism is to provide a reduction of some kind of problematic discourse or theory to an unproblematic one. And one of the things that Butterfield and Gomes think that we've all missed is that we were doing space-time functionalism when we were just doing, say, kind of old-fashioned relationism in Newtonian mechanics. So, the kind of Newton-Leibniz debate was an example of Leibniz reducing problematic discourse, what about space-time, to an unproblematic one. So something like Barborian relationism reduces problematic space-time theories to unproblematic theories involving, for example, the dynamics of fields and bodies. So they're going to see this kind of functionalism as much more common and much less kind of revolutionary than some people have sort of claimed it to be. So questions you might have about that analysis. I mean, in a sense, it's clearly right in certain examples. It's clearly a thing that we might be really interested in doing when we have two theories at different levels. But you might question, should reduction always be the aim of functionalism in physics? You might think that maybe sometimes we can be doing that work that they acknowledged was hard and foundational of giving a functional analysis without the next step, that's the reductive step. Related to that, I think, is the question of whether it's helpful to think of the terms that you're trying to functionalize in the theory that you're trying to functionalize as problematic, and the ones that in the lower level theory is unproblematic. I mean, the literature on space-time functionalism is intimately connected with the question of recovering classical spacetimes from quantum gravity. And it's terribly odd to think that the language of classical spacetimes is problematic and the language of quantum gravity is unproblematic. Butterfield and Gomes are very aware of that. And then the other question is sort of how does novelty or emergence fit into the picture in general? So let's move on to our second strand of functionalism. Prior to this kind of booming literature on space-time functionalism that exists at the moment, the place that the average undergrad doing a philosophy of physics course might have come across the notion of functionalism would have been in the Everett interpretation literature, the many worlds interpretation literature in the philosophy of quantum mechanics. So here's one thing you might think is a problem for somebody who wants to say that we can get multiple parallel universes, multiple worlds, right, out of quantum mechanics. One of the things you might worry is that, look, there aren't any multiple worlds or cats in the theory in the first place. The theory just describes an evolving wave function. And normally when you talk about quantum mechanics, the wave function with its superpositions is supposed to be representing a single particle or a single system. So there's a kind of multiplicity that you need to get many worlds. It just isn't there in the theory. And Wallace famously comes along and says, look, if we're functionalists of this sort of Dennettian stripe, we can get round this. Classical structures get recovered from the quantum state just via functionalism. So let's give a functional analysis of the concept of the cat that Schrödinger half killed, right? And let's say that, look, the concept cat can be functionally picked out by theories of zoology and biology and maybe folk theories of animal psychology. We've got a whole bunch of ways of picking out a kind of functional analysis of cats. And now you just say, well, if something behaves like a cat, it's a cat. And so if I can pick out two structures in the wave function, for example, that fit the functional analysis of cat, I can say that there are two cats. This is the move that Wallace makes, even if it isn't the case that I want to say there are two sets of particles, for example. If something behaves like a macro object in a classical theory, it just is one. And then that gets explicitly associated with Dennett's real patterns ontology. So the things that are then the realizers of the functional role tend to be patterns. But despite the poll just before I came on being wonderfully appropriate, I'm not going to particularly be talking about real patterns ontology today, but I think we may hear more about it later. So how should we evaluate that kind of picture that Wallace says is inspired by Daniel Dennett next to the kind of Lewisian picture that Butterfield was advocating? Now, if you start thinking about this too much, you go down a kind of metaphysical and epistemological rabbit hole, right? Because Dan Dennett exegesis is really hard. I had a wonderful MA student who taught me this. He did a brilliant job of Dan Dennett exegesis, made me realize how subtle the whole thing was. Dennett's implicit metaphysics and epistemology is implicit and potentially not very realist and kind of pragmatist and quite complex, and arguably diverges very considerably from something like David Lewis's terribly explicit framework. But I don't think we have to go into that when we're thinking about, this is why Dennett crops up in inverted commas in places. I don't think we have to go into that when we're talking about philosophers of physics. I don't think that, I mean, and perhaps we should push on this, but I don't think, as he intends it, someone like David Wallace's realist commitments are very terribly different from someone like Jeremy Butterfield's. So brushing all of the Dennettian subtlety under the carpet, what characterizes in the philosophy of physics that more Dennettian approach? Well, look, one thing you can say is that in that kind of multi-step process that Lewisian process that Butterfield describes, the Dennettian functionalist is more interested in step one, the bit where we give the functional analysis. They might be interested in finding out what instantiates the functional role once we've done it, but that doesn't have to be the primary aim. Rather, just establishing that something fills that role is sufficient for existence claims. And you don't need to know what that something is, and you don't need to say anything about the something. Indeed, it sort of goes the other way around. I mean, the very fact that we clearly live in a world where something instantiates the role, so it shows that something instantiates it and exists. There's clearly something behaving like a cat. In part, that's what's important about the Dennettian analysis. And part of the point of functionalism here is to be extremely liberal. This is a traditional feature of functionalism. You can be extremely liberal about what might fill the role. And there could be loads of approximation and idealization and emergence in the relation between two theories. Another difference of kind of emphasis is that higher level structure is often treated as the unproblematic starting point in this kind of Dennettian analysis. So can you reconcile not quite Dennett and Lewis, or Dennett in inverted commas and Lewis? I think you absolutely can. So to a large extent, the difference between the above characterizations is sort of a matter of emphasis names. So, you know, this kind of Lewisian picture saw the whole point of functionalism as reduction. For the Dennettian, the big point of functionalism is probably that first step where you've given a functional analysis, you've understood the higher level theory better. It can also underpin interpretive claims about the higher level theory without necessitating reduction. And as a result, the Dennettian puts more emphasis on what you might call emergence than reduction. But you can insert that into the Lewisian account by talking about ways in which functional roles could be realized by relevantly emergent structures if we had that kind of detail. So I want to give you an example, and I say it's a slightly techie philosophy of physics example of how I think the Dennettian approach might give us more illumination about a foundational dispute. So let me try and do that briefly. Hopefully it'll be of some use. So way back when, I got myself embroiled in a debate that I found really puzzling, because Simon Saunders, who I have enormous respect for, and I both wrote papers about what you should say about the space-time structure of Newtonian theories. We both wrote papers about what you should say about them in light of something that Newton himself knew about, that we've known about for ages, Corollary 6 of Newton's Principia, which basically says that you can't detect uniform acceleration. If bodies moved in any manner amongst themselves or urged in the direction of parallel lines by equal accelerative forces, they'll all continue to move amongst themselves after the same manner as if they'd not been urged by those forces. So, a great puzzle is that, about Newtonian mechanics is that Einstein's elevator, a freely falling elevator in a gravitational field, is just as undetectable from one at rest as Galileo's ship was. There's an accelerative symmetry that's kind of not acknowledged in Newtonian mechanics. And that plays very strangely into a very long-standing debate that hopefully even those of you who haven't done much philosophy of physics have probably heard about the right space-time setting for Newtonian theories. So there's a kind of standard bit of philosophy of physics that says there are different geometrical structures that could represent Newtonian physics, the space-time of Newtonian physics. And one is Newtonian absolute space. And in Newtonian absolute space, spatial points persist from one time to another. And if you're moving with a constant velocity, you're not accelerating with respect to the kind of absolute identity lines of the space-time points, but there's a matter of fact about how fast you're moving. Now, Newtonian absolute space looks like it has obsolete structure, because we know that in Newtonian mechanics, you can't tell how fast you're moving, but there's this metaphysical matter of fact about how fast you're moving. So the standard argument that you kind of give to, in kind of philosophy of physics 101 is that this is a kind of classic example of a kind of a redundant bit of structure in a physical theory. And the fact that we can't detect absolute velocities in principle as well as in practice means that we should move to neo-Newtonian space-time, where there's no identity of spatial points over time, just a standard straight line inertial motion. And then there's another kind of Newtonian space-time theory you could have, which is Newton-Cartan theory, which doesn't have any inertial structure at all, doesn't have any kind of absolute straight line motions. It's much more like general relativity, and it has a curved geometry with freely falling bodies following the inertial paths laid out by the curved geometry. And we've known for a while that you could write down a Newton-Cartan theory and it's empirically equivalent to Newtonian space-time. But the connection between that and kind of accelerative symmetries has been a little bit of a puzzle. So I wrote a paper about this accelerative symmetry saying, look, if you acknowledge Corollary 6 alongside other symmetries, you should be taken to Newton-Cartan theory, this curved space-time theory of Newtonian mechanics. And in just the same way that we never thought that we should really have believed in Newtonian absolute space in the first place, we should never have believed in neo-Newtonian space-time in the first place. There's a real sense in which, given that Corollary 6 is in Newton's Principia, the right space-time structure for Newton's own theory is a curved theory, is Newton-Cartan theory. And at exactly the same time, well, actually, he wrote his paper slightly before mine. I had read his paper. Simon Saunders was arguing that that same accelerative symmetry should lead us to formulate Newtonian mechanics on a much less structured space-time called Newton-Huygens space-time, sometimes called Maxwellian space-time. And that space-time's only got enough structure to tell you if you're rotating. It can't tell you if you're accelerating, and obviously can't tell you if you're moving with an absolute velocity. It doesn't have inertial structure. It doesn't have natural motion structure beyond that rotation structure. In fact, its dynamics is all defined in terms of relative accelerations. It's written in this kind of vector relationist format. So it looks on the face of it a very different theory with a very different space-time structure. David used to like to ask us both how on earth we could both start from the same premises and reach a different conclusion, which was an excellent question to ask. And neither of us had a terribly good answer for him. And then David Wallace and also Jim Weatherall in a kind of paper started exploring the connection between these two theories, trying to understand how you could sort of incorporate the same elements of Newtonian mechanics and reach such different conclusions about space-time structure. And Wallace then wrote this nice paper where he starts from Saunders's account, which is this account with the minimal space-time structure, and very, very little to kind of hang your hat on in terms of fundamental space-time ontology. And he says, look, when you look at this theory as a theory of the universe as a whole, that theory just doesn't have any inertial structure. I'm going to think of inertial structure and space-time structure as quite connected. But he points out that you can do some modeling in that theory. You can ask about the dynamics of a sufficiently isolated subsystem of the universe. And you can point out that if you have a sufficiently isolated subsystem, if you do proper modeling, you get what's functionally equivalent to what plays the role of a natural state of motion, an inertial frame within the theory. And the dynamics of that system relative to the center of mass of the rest of the universe transform under the Galilean group, a smaller set of symmetries, not the Maxwell group. I won't worry too much about the last point, particularly because it's cut off. But the point is that when you start thinking about how to actually model systems within this very minimal universe, what you get is something that's functionally picking out the role of a local inertial structure, this thing that Saunders said wasn't fundamentally in the theory. And Wallace goes on, and this is something that Jim Weatherall did too, to show that the formalism of Simon's theory, this vector relationist theory, and Newton-Cartan theory are interdefinable. So he shows that the structure probed by a test particle in Saunders' theory is exactly this, what we call the space-time structure, the inertial structure of the geodesics and the Newton-Cartan connection. And that structure is sufficient to specify a vector relationist theory. So he basically does a kind of classic interdefinability proof. And what he concludes is that this theory with no space-time structure, or very little space-time structure, merely a rotation standard, and this theory with quite a rich dynamic space-time structure, Newton-Cartan theory, which looks more like general relativity, he concludes there is essentially no difference between Newton-Cartan theory and Saunders' relational version of Newtonian dynamics. At the formal level, the latter can be reformulated in the former. At the substantive level, the inertial structure of Saunders' theory is well defined and coincides with that defined by the Newton-Cartan connection. So far from it being, from Simon and I starting with the same premises and reaching different conclusions, Wallace's claim is we functionally again, reach the same conclusion. And functionalism is playing a key role in an argument like that. If you grant that defining inertial structure is the key spatiotemporal role that's played by a space-time connection, so the idea is that defining natural motions is the main thing space-time structure does here. You give a functional analysis. If a connection, a piece of geometrical structure, plays the role of picking out the natural motion structure, it represents space-time structure. You then go on to establish that vector relationism contains within it the resources to define that structure, and hence the space-time connection. And the functionalism leads to the conclusion that vector relationism posits a role filler, the inertial space-time structure, in just the same sense that Newton-Cartan theory does. They just mathematically represent that role filler differently. And given that each theory can be formulated in terms of the other, they're then one and the same theory with the same interpretation, according to Wallace. And part of that argument comes from yet another use of functionalism in Wallace's paper. So one of the things he's thinking about is how we should think about the space-time structure that something like the Earth feels in the solar system. How we should think what the natural kind of inertial structure of subsystems of the universe is for subsystems at different scales. So for example, the Earth-Moon system follows a natural path in a circle around the sun. It surveys the inertial system defined by the sun. And he wants to say that, and But of course, the moon surveys a slightly different inertial structure, right? It has a different set of natural motions. So Wallace wants to say, look, the large-scale space-time structure defined by the sun is space-time in just the same functional sense in which smaller scale space structure is space-time structure. And that makes really good sense of practice in astrophysics, what we actually do when we model. So part of his point is that we come by the complete, what you might think the fundamental, the super fine-grained Newton-Cartan inertial structure in a global theory, just by applying the same methods that we use for a scale relative or approximate structure. The same kind of functional analysis, what's playing the role of picking out the right paths for some given body. So what does that mean about our previous debate? How well does that fit with strict Lewisian functional reduction? Do we have reduction here at all? Should we see Newton-Cartan theory as reduced to vector relationism here? Well, from the perspective of this kind of very unspaced-timey theory, vector relationism, a fairly complex structural feature of the dynamics ends up filling the role of defining the space-time structure, the inertial structure. If one had prior reasons for thinking the vector relationist formulation was ontologically fundamental, for example, you might think there was a reduction here. You'd reduce space-time structure to relational dynamics. But that wasn't Wallace's main aim. He doesn't have a view about which of these things is more fundamental. Instead, he wants to just use functionalism just to show that the structure posited by one theory is just the same structure with the same function as that posited by Newton-Cartan theory. Strictly, he's literally done an interderivation of the two theories, a 1-1 relationship between models of them. Actually, it's not a 1-1 relation if you look at Lefebvre's work, but anyway. Strictly, he's engaged in a kind of two-way Nagelian reduction, at least between kind of classes and models in one theory and models of in the other theory. He shows that two apparently divergent formulations are interderivable. But you didn't need the functionalism to establish the bridge laws. It wasn't this Lewisian functional analysis that was telling you how to relate models. That was actually just showing that you had empirically equivalent models of the two theory and they were interderivable. Functionalism actually came in at the level of interpretation. It came in at showing that you had these two equivalent theories and that they could be interpretationally equivalent as well, showing that you don't have to think of this very austere vector relationist theory as a theory with only Maxwellian space-time structure. And if you go back to this story about thinking about scale relative structure, you can think about galaxies surveying inertial structure, you think about the Earth-Moon system surveying the inertial structure of the sun. You see functional analysis being used here as well, right? It's being applied to large-scale structure as well as fine-grained space-time structure. The plausible realizers of those structures are different. Large-scale space-time structure gets realized by finer-grained space-time structure in this kind of local piecemeal way. Fine-grained structure, maybe, is realized by the vector relationist framework. But the sense in which there's a kind of Dennettian theme here is that finding the realizer isn't really an essential part of the functionalist process. The thing that we're interested in is that there is a realizer, that something plays the role of, say, space-time structure. And the realizer could be many things, including a piece of non-fundamental structure itself. And it turns out that actually the sense in which Wallace uses the word emergence tends to just refer to that feature, that fact that, when you have kind of emergent stuff, it's cases where, the story about how exactly what realizes something is a bit messy. And the thing that realizes isn't fundamental. He tends to use the word emergent for that. So all this emergent structure that we have, for example, inertial structure around the sun. So functional analysis doesn't lead to emergence, but it does allow for it. And I think that whole framework, which, as I say, I think was illuminating, taught us quite a lot about how to think about space-time structure in Newtonian theories and thereby space-time structure in other kinds of theories. I think that whole piece of work is only really comprehensible under the framework of this slightly more Dennettian functionalism. If you think about what's going on there purely as Lewisian functional reduction, I think you're missing a lot of the analysis. So while there are doubtless many cases in which Lewisian functional reduction gives a good understanding of applications of functionalism in space-time physics and in other bits of physics, and doubtless in some other, although I think it gets messier outside of physics, but focusing on that to the exclusion of a less reductive kind of functionalism is to miss interesting applications and to crowd out some of the space for a kind of emergence. That's it. Thank you very much.